Okay, third and final video. Last two problems take a little bit of time. And what you can see here on number 6 is that we have one with definite bounds here. We hadn't really dealt with that other than the ellipse problem. So one of the first things you should see is that 4x squared plus 9 is not in the right form. And you might have noticed that I've got a 3/2 power down here. Well, remember that a 3/2 power is something which is cubed and then square rooted, or vice versa, square rooted and then cubed. So it still works. It's still a square root. However, we need to get the 4x squared plus 9 into the correct form. So in order to do that, we have to do a little bit of algebraic manipulation here. So let's go ahead and rewrite our integral. This bound up here, 3 cube roots of 3 over 2, does not look fun to deal with. Whoops. So we're going to rewrite what's underneath of this by factoring out a 4. Because I need that to just be x squared there. When I factor out a 4, I have to factor it out of the 9 as well, so that'll become 9/4. And that whole thing is still raised to the 3/2 power. Now at least I've got the x squared part plus the 9/4, and the 9/4 is going to become our a squared. So at least we're in the correct form. Let's go ahead and finish off taking this 4, however, out. 4 to the 3/2 power, remember it's the square root of 4. Do the half power first, which is 2, and then cube it, which is 8. So I'm going to have a 1/8 on the outside. Alright, so I've still got an x cubed on top, and then I've got x squared plus 9/4 to the 3/2 power. And again, if you felt like you needed to, you could rewrite that as the square root of x squared plus 9/4 and then cube the whole thing. And it does give us the correct form. So we're going to go ahead and do, that's an x squared plus a squared. We're going to do a trig substitution where x is a tangent and a is 3/2 tangent theta. So we know we're going to need dx, which will be 3/2 secant squared theta d theta. Might want to write a little bit smaller on this one just to make sure you have enough room. Should be able to fit it on the page here, but we'll just make sure. Alright, let's go ahead and start doing some replacing. So 1/8. I'm going to leave the bounds alone for now because we are going to have to replace those. X cubed is going to be, let's see, that's 3/2 cubed, which is 27/8 tangent cubed theta, over x squared, which is going to be 9/4 tangent squared theta, plus 9/4, all of that to the 3/2, and then dx is 3/2 secant squared theta d theta. Now let's go ahead and start taking a look at these bounds, because we do have to change the bounds. So remember, I am plugging in 0 and 3 cube roots of 3 over 2 in for x, and we'll solve that. So I'm going to plug 0 in. I could divide both sides by 3/2, and that gives me that tangent theta equals 0. And that's going to be when theta is 0. If I plug in 3 root 3 over 2 equals 3/2 tangent theta, well, I could multiply both sides by 2, that'll go away. I could divide both sides by 3, that'll go away. Fortunately, now we have that tangent theta equals the square root of 3. That is something that we know from our unit circle. And theta then would be pi/3. So I now have my new bounds. 0 to pi/3, and that'll be, those actually look easier to deal with. The integral itself currently doesn't, but we'll fix that soon. So we're going to have 1/8 of the integral from 0 to pi thirds. Let's simplify our denominator. So our numerator is still 27/8 tangent cube theta. Still going to have this 3/2 secant squared theta d theta on the right. I can factor a 9/4 out of the denominator, but I do have to take 9/4 to the 3/2 power. So take the square root first. Square root of 9/4 is 3/2, and then cube it. Well, that gives us 27/8. That's nice. That's going to leave us with that tangent squared. Remember, there'll be a +1 there where that 9/4 was. Tangent squared plus 1 is secant squared. Well, again, take the 3/2 power. So take the square root of secant squared, which is secant, and then cube it, which gives us secant cubed theta. Alright, let's try and make this a little simpler looking now. So the 27/8 are going to go away. The secant cubed on the bottom, I'm going to get rid of both of those secants right there and all but one of those. So now let's go ahead and rewrite this. This will be 1/8 integral from 0 to pi thirds of, let's see, I've still got all the tangents. And I will have a secant left in the denominator. And I lost my 3/2, so I'll multiply by 3/2 there. So that's actually going to give me a 3/16 out in front. Alright, so once again I'm to the point where I don't see any easy Pythagorean identities to use here, so I'm going to change everything into terms of sines and cosines and hope that that helps us out here. So tangent cubed would be sine cubed over cosine cubed of theta. Secant is 1 over cosine of theta. So let's see, if I bring the 1 over cosine theta up, flip it over and multiply, the cosine is going to go on top, which will get rid of one of the cosines from the bottom. So we should have 3/16 integral from 0 to pi thirds. The sine cubed is going to remain on top. I should now have cosine squared and the denominator. Now here's where a little bit of ingenuity is going to come into play. Maybe not something you would normally think to do here, but this is the way it's going to work out the best. I'm going to take and I'm going to separate the sine cubed to be sine squared times sine. And while you may have actually thought of that part, it's the next part that might not have been what you would normally think of. So I see sine squared over cosine squared. My first thought is make that tangent squared, but then I have tangent squared times sine. That doesn't really help us very much. But what I can do is I can change the sine squared on the top to be 1 minus cosine squared, and that's going to be much more useful. So we'll get 3/16 0 to pi thirds for our integral, 1 minus cosine squared theta over cosine squared theta sine theta d theta. So the reason that that's going to be helpful is because now I can do a standard U substitution. Okay, I'm going to let U equal cosine of theta. And I'll show you why in a second here. So that makes du negative sine theta d theta. So d theta equals du over negative sine theta. So now let's show why this is actually useful. So I'm going to have 3/16 integral. I am going to have to change the bounds again. And the reason I'm changing the bounds all the way down is because it's going to be much easier to do it this way than to not change the bounds and then have to go back through a U substitution, through a trig substitution, all the way back to the original. It'll be much more challenging. Alright, so if U is cosine, I'm going to get 1 minus U squared on top over U squared sine theta, and d theta is du over negative sine theta. So hopefully now you can see that the sine thetas are going to go away. The 1 minus u squared over u squared we can actually simplify algebraically because a singular denominator we can separate the numerators on top of, and this will actually simplify relatively easily. Let's figure out our new bounds. If we plug 0 in for theta, because those are theta values, cosine of 0 is 1. So my new lower bound is 1. And if I plug in pi thirds for theta, cosine of pi thirds is a half. And while I know those bounds are wrong, I have this negative sign right there that I can use to flip the bounds. So if I pull the negative sign out, I'll flip the bounds over, and what we get is 3/16. The sine thetas will go away of the integral from 1/2 to 1. I'm flipping the bounds because of the negative sign. Of 1 minus u squared over u squared. Well, that's 1 over u squared, which is u to the negative 2, minus u squared over u squared, which is minus 1 du. That now becomes a much simpler thing to take an antiderivative of. And remember, we don't have to go back at all because we've changed the bounds as we've been going along this thing. So this should be pretty easy to go ahead and finish off now. So I got 3/16. Antiderivative of u to the negative 2. Raise it by 1 is u to the negative 1. Dividing by negative 1 will give us negative 1 over u. And then the antiderivative of 1 is u from 1/2 to 1. Alright, I personally prefer to pull this negative sign out of the parentheses there. So I'm going to have negative 3/16 1 over u plus u. Sorry, not plus 1. From 1/2 to 1. Alright, let's plug our values in and we will be done. So, plugging in 1, that's going to give me 1 over 1, which is 1, plus 1 is 2. Plugging in a half for u, I get 1 over a half, well that's 2, plus a half, 2 plus a half is 5 halves. So I get negative 3/16, 2 minus 5 halves is negative 1/2, so we end up with positive 3 over 32. Alright, again, hopefully you can see that that was much easier changing the bounds as we go than having to try and take something in terms of u, go back into terms of theta, and then go back into terms of x. And who wants to plug in 3√3 over 2 if we don't have to, right? So hopefully that was the much easier way. Alright, one more. So the last problem doesn't look at all like it's in the right form. I've got this square root of 3 minus 2x minus x squared. U sub will certainly not work here because I'd end up with an extra, I'll end up with negative 2x minus 2, and that won't get rid of that x on the top. So we are going to definitely have to use some ingenuity here. First thing people usually think of is, well, can I factor the denominator? Well, you can actually factor what's underneath of there, but that's not going to help because then you'll end up with a binomial times a binomial underneath of the square root. Yes, you can separate those, but it's not going to do you any good. So what you have to do, and again, this is a little bit tricky. Okay, great. We're going to take that 3 minus 2x, 3 minus 2x minus x squared, and we're going to rewrite that. First thing I'm going to do is I'm going to change the order. Minus x squared minus 2x plus 3. And I'm actually going to separate this to minus x squared minus 2x plus 3. Some of you may know where we're going with this already. I don't like dealing with a negative in front of my x squared, so I'm going to pull that out to the front. So what I'm trying to do is I'm trying to get what's in this parentheses to be a perfect square of some kind, because then I'll have the form that we're used to seeing underneath the square root. So in order to do that, I have to go to our old friend completing the square. Remember, the idea was you take and divide that middle term in half, and then when you divide it in half, you're going to square it to give you what's left. So 2 divided by 2 is 1, squared is 1. Now here's the problem. I just arbitrarily took and added 1 to an expression. Well, you can't just add 1 to an expression. You're changing it. So what I really need to do is I need to counter that. And I actually didn't add 1. This is the really tricky part. This negative right here has to get multiplied by that 1 right there. So really I just subtracted 1 from this entire thing, which means I arbitrarily now need to add 1 in order to balance this out. And I know this is kind of a really tricky thing there. So this is now in the correct form. This factors. This is a perfect square trinomial. It would be x plus 1 times x plus 1, or x plus 1 squared, and then on the outside I get plus 4. So what I really have, if I rewrite that, is 4 minus x plus 1 squared. Okay, we're almost to where we need to be. I would prefer not to have that parentheses with the x plus 1. I would rather just have it be x, but we can't do that. But what we can do is we can change the x plus 1 into some other variable. So I'm going to let u be x plus 1. And no, we're not ready to take an integral or anything. This is not a standard U substitution that we're used to seeing. I'm just letting the variable u be our substitution. You could have put in a y or a z or anything else you wanted to at this point. But u is going to be x plus 1. Alright, so now let's see how this helps. Let's do a couple substitutions here. I'm going to have the integral. I know what's under my square root is this thing right here. Okay, that's not our answer, so let's erase that part. But this is what I'm going to have underneath the integral. I am going to plug u in for x plus 1, so I have 4 minus u squared. And I've got this x on top that I still have to deal with, and I've got this dx out here that I still have to deal with. Well, we're going to change those. The x on top, I need to put in terms of u. Well, I can do that because this, over here, I can solve for x by subtracting 1 on both sides. So x is u minus 1. So I'm going to put u minus 1 in its place up on top. And then du, dx is just going to be du if I take the derivative of both of those. So I've got du. Now we're in the correct form. We're in the form that we need to have in order to do this problem. Okay. So now we're going to go back to our trig sub. And I've already used x in this case and u. So instead of letting x equal our trig substitution, now it's going to be the u value that equals our trig substitution. So u, and let's see, this is 4 minus u squared. That follows the form of sine. So that's going to be 2 sine theta. So du, because we know we're going to need that in this case, is going to be 2 cosine theta d theta. Whoops. Keep doing that. Alright, so now let's see how that's going to help us. So on top here, u is 2 sine theta, so I'll have 2 sine theta minus 1 over square root of 4 minus squaring the u part is 4 sine squared theta, and du is 2 cosine theta d theta. Okay, let's simplify. So we got 2 sine theta minus 1, oops, forgot the integral, over. So we can factor the 4 out, square root the 4, we'll get a 2. We can change what's left under there to 1 minus sine squared, which is the same as cosine squared. Taking the square root of that gives you cosine theta. Hopefully you followed that. This will actually simplify quite nicely. Because what you should be able to see now is I've got 2 cosine theta and 2 cosine theta. Those two things are going to go away. which is going to leave us with only the integral of 2 sine theta minus 1 d theta. So the antiderivative of 2 sine theta will be negative 2 cosine theta. The antiderivative of 1 is theta, plus c. We do have to go back to our right triangle. I didn't really leave myself enough room up there, so we'll draw the right triangle down here. Here's theta. So what I know from my U sub is that sine theta is U over 2. So sine is opposite over hypotenuse, U over 2. So it should not come as a surprise that when you use Pythagorean theorem, you're going to get the square root of 4 minus U squared. So we're going to go ahead and substitute those things in. I do know that theta, I have to solve that one, as the inverse sine of U over 2. So let's go ahead and substitute. So we've got negative 2. Cosine is going to be adjacent over hypotenuse, so that'll be square root of 4 minus U squared over 2 minus theta, which we just solved for, which was inverse sine of U over 2 plus c. But of course we didn't start off in terms of U, we actually started off in terms of x. So we're going to go back up here and notice that U was x plus 1. So everywhere we have U, we're just going to plug in x plus 1. So I do notice that I can get rid of these 2's. So what we should have is negative square root 4 minus, plugging in x plus 1 for U squared, minus inverse sine x plus 1 over 2 plus c. And obviously you could go ahead and FOIL out the x plus 1 underneath of there and combine like terms, but this is plenty. And that is the answer. Alright, plenty enough videos. Should be good.